So the gas is getting expanded from the stagnation state. Its velocity will increase, Mach number will increase, right? Pressure and temperature will decrease. It's changing its state from state 1 to state 2 by polytropic process defined by n is equal to 1.32. For this polytropic process, for this path, this n is given. Let's discuss few problems based on introduction lecture of gas dynamics, which will help you to build the fundamental. And in the end, I will discuss frequently asked question too. So let's see first question. Hydrogen gas in a cylinder at 7 atm 300 Kelvin is expanded isentropically through a nozzle to a final pressure of 1 atm. Assuming the hydrogen to be a perfect gas with gamma is equal to 1.4, determine the velocity and Mach number corresponding to the final pressure. Also find the mass flow rate through the nozzle for an exit area of 10 centimeter square. So in a flow process, whenever tank, cylinder, reservoir, settling chamber, these words are written, then properties at that section will be stagnation property, right? Because gas is at stagnation state. So that's why this is P naught, which denote stagnation pressure by P naught. We use this subscript naught for stagnation property. P naught is equal to 7 atm. Similarly, this is T naught. Right? So the gas is getting expanded from the stagnation state. Its velocity will increase, Mach number will increase, right? Pressure and temperature will decrease, correct? So for Mach number, let's apply relationship between pressure and Mach number. Derivation we already did in the lecture. I will directly write the formula. P naught by PE is equal to 1 plus gamma minus 1 upon 2 me square power raised to gamma upon gamma minus 1, right? P naught is 7 atm, P exit is 1 atm. 7 by 1 is equal to 1 plus gamma is 1.4 power raised to 1.4 divided by 0.4. So this will be power raised to 1 by 3.5 is equal to 1 plus 0.2 me square. So we got m exit 1.928. So this is the exit Mach number. Correct? Now we have to find out exit velocity too. How we'll get that? Velocity is equal to Mach number into speed of sound. Now, in the definition of speed of sound, what is that term which we are using? That is local speed of sound, right? It means this speed of sound A will be at exit location. So it will be under root gamma r Te. So we need to find out exit temperature too, correct? So let's find out. We know T naught by Te is equal to 1 plus gamma minus 1 upon 2 me square, correct? T naught is given. What is T naught? Tank temperature 300 Kelvin. So let's substitute 300 divided by Te is equal to 1 plus 1.4 minus 1 upon 2, that is 0.2 into 1.928 square. So from here we got exit temperature 172 Kelvin, right? Now we can find out exit velocity. VE is equal to Mach number 1.928 into speed of sound, that is under root gamma RT. Gamma is 1.4. What about R value? because in most of the problem they used to give air. So many students are getting habitual of using R value of air, and then they are getting wrong answer, and they are telling that we are not able to get the correct answer in spite of applying correct approach, right? So you have to see which gas is given. So hydrogen is given. What about R value for hydrogen? Formula is R naught by M 8314 divided by 2, right? That is 4157 joule per kilogram Kelvin. So we can substitute here 4157 into T exit 172. Speed of sound A is under root gamma R T, right? So V exit is equal to 1928 meter per second, right? Now we have to find out exit mass flow rate. Mass flow rate will be constant, right? At each and every point it is constant. So let's find out the mass flow rate at exit. What is the formula? Rho A V, right? Density at exit, exit area, exit velocity. This we can write by using equation of state P exit upon R T E into exit area into velocity, right? Exit pressure is 1 atm, 101325 Newton per meter square upon R is 4157 joule per kilogram Kelvin into T 172. Exit area is given 10 centimeter square. So 10 into 10 raised to power minus 4 meter square into exit velocity 1928 meter per second. So from here we will get mass flow rate at exit is 0.273 kilogram per second, right? Let's move to next question. In this question, air in a cylinder changes state from this pressure and temperature to a final pressure of this according to the process PV raised to 1.32 is equal to constant. Determine the entropy change associated with this process. Assume air to be an ideal gas with Cp is equal to 1004 joule per kilogram Kelvin and gamma is equal to 1.4, right? In this question, few students are getting confused that gamma and N both are given, right? Then what we have to do in such case, right? See, if we have air with gamma is equal to 1.4 obviously, so it is not necessary that air will always change its state from state 1 to state 2 by isentropic process only. There may be number of process by which state change can be achieved, correct? So the system is changing its state from state 1 to state 2 by polytropic process defined by n is equal to 1.32. For this polytropic process, for this path, this n is given, right? So to find out the change in property, we have to apply polytropic formula, polytropic relations, right? So they are asking entropy change. So delta S formula we already know. Delta S is equal to Cp ln T2 by T1 minus R ln P2 by P1. So we just have to find out delta S. So we need this ratio, right? So this is P1, 101 kilopascal, T1, 310 Kelvin, P2 is 1100 Kelvin, kilopascal, correct? So what is this ratio P2 by P1? 1100 divided by 101, 10.89, right? Now we need temperature ratio. So we know that P2 by P1 power raised to n minus 1 upon n is equal to T2 by T1. So from here we can find out this ratio T2 by T1 so that we can substitute here, right? So T2 by T1 is equal to 10.89 power raised to n is 1.32. 1.32 minus 1, 0.32 divided by 1.32, correct? So this will be 1.784. Now we can substitute this ratio here. So delta S is equal to 1004 into Cp ln T2 by T1, ln 1.784 minus R 287 ln 10.89, right? So we will get delta S is equal to minus 104 joule per kilogram. Let's move to next question. A 15-meter cube tank contains air at P1, this much, T1 500 Kelvin. The air is discharged into the atmosphere through a nozzle until the mass of the air contained in the tank is reduced to 1/2 of its original value, right? So M2 will be half of M1. Assuming that the process is adiabatic and frictionless, means isentropic, calculate the pressure and the temperature of the air remaining in the tank. Consider a calorifically perfect gas, right? So P1 is equal to 5 into 10 raised to power 5 Newton per meter square. T1 is equal to 500 Kelvin, right? We have tank. In this, we have air, right? So half of the gas is getting discharged, right? So here we have state 1, P1, T1, right? M1, capital V, volume V1. This state is getting changed, right? Now at state 2 again we have air, but mass is half of initial. So at state 2 we have P2, T2, which we have to find out, M2, volume V2, right? So here what few students are doing, that when mass is getting discharged and it is reducing to the 1/2 value, they are thinking that volume will also change. See, it is rigid tank, right? Volume will not change. V1 and V2 both are equal, right? Because it is rigid tank, whatever the gas is left after getting discharged, that will occupy the tank volume, right? So volume will be constant. So we have adiabatic and frictionless process, means isentropic. So we can apply isentropic relation. P2 by P1 is equal to rho 2 by rho 1 power raised to gamma. So P2 by P1 is equal to rho 2 is m2 by v2, rho 1 is v1 by m1, it is 1 by rho 1, so v1 by m1. This will get cancel out. We will get p2 by p1 is equal to m2 by m1 power raised to gamma. Right? So p2 by p1 is equal to m2 is half of m1, so half power raised to 1.4. So p2 is equal to 5 into 10 raised to power 5 into half power raised to 1.4. So p2 is 1.89 into 10 raised to power 5 Newton per meter square. Right? Now for temperature T2, we can again apply the isentropic relation between pressure and temperature. So that is T2 by T1 is equal to P2 by P1 power raised to gamma minus 1 upon gamma. So T2 by T1, P2 by P1, this ratio we already have, half power 1.4, half power gamma. So it will be 1 half power gamma minus 1. Gamma and gamma will get cancelled out. Gamma minus 1 is 0.4. So T2 will be equal to 500 into half power 0.4. So temperature T2 is 378 Kelvin. Right? So at state 2, we got the pressure and temperature. This question can also be solved in another way. We can write equation of state at state 2, that is P2 V2 is equal to M2 RT2. Equation 1. We can write equation of state at state 1, P1 V1 is equal to M1 RT1. State 2. Divide both, right? This will get cancelled out. Volume is again constant. R and R will get cancelled out. We will get P2 by P1 is equal to half T2 by T1, right? So one equation we got from here, and one equation we have from isentropic relation, that is P2 by P1 is equal to T2 by T1 power raised to gamma upon gamma minus 1. Right? We have two equation, two unknown. We can solve for P2 and T2. So you can try by this way, right? You will get same answer. So we can follow this approach too. Right? Next question. Compute the temperature rise at the nose of an aircraft flying with Mach number 2 at an altitude where temperature is 223 Kelvin. Right? So we have to find out temperature here at the nose. Mach number is 2. Surrounding static temperature is 223 Kelvin. Right? Here at nose, air will be at stagnation state. Right? So here temperature will be T naught. Correct? We have to find out temperature rise. So first let's find out T naught, stagnation temperature, because air will be at stagnation state at the nose of the aircraft. Right? So let's apply the relationship between the Mach number and temperature. T naught by T is equal to 1 plus gamma minus 1 upon 2 m square. So we have to find out T naught. T naught is equal to 223 into 1 plus 1.4 minus 1 upon 2, 0.2 into Mach number is 2. So T naught is equal to 223 into 1.8, that is 401.4 Kelvin. So they are asking temperature rise, delta T. So delta T is equal to T naught minus T, that is 401.4 minus 223, that is 178.4 Kelvin. So at nose, this will be increase in temperature, right? Rise in temperature, delta T is 178.4 Kelvin. So this thing you have to remember whenever they are asking properties at the nose of the aircraft, we have to find out stagnation property because air will be at stagnation state. So they were asking rise in temperature, so that's why we found delta T, T naught minus T. Next question. Air flows isentropically through a nozzle if the velocity and temperature at the exit are 390 meter per second and 28 degrees Celsius. So exit velocity is 390 meter per second. Exit temperature is 28 plus 273 is equal to 301 Kelvin. Determine the Mach number and stagnation temperature at the exit. Right. So what we have to find out? ME, Mach number, and stagnation temperature. Stagnation temperature for an isentropic flow remains constant. So whether you find at any other location or if you find at exit, it will be same. This concept we learned in the lecture, that T naught, stagnation temperature, will be constant throughout the isentropic flow. Correct? So we have TE and we have V. So for Mach number, M exit, VE divided by A, right? What is this A? In the definition of A, again it is local speed of sound. Why we are using local word? Because A will be, if we are finding out exit Mach number, A will be corresponding to exit location. Correct? Exit temperature is given, velocity is also given. So 390 divided by under root gamma R TE 301. So that will be 1.12. So we got Mach number. We have to find out stagnation temperature. So again we can apply T naught by T is equal to 1 plus gamma minus 1 upon 2 ME square, right? So T naught is equal to exit temperature 301 multiplied by 1 plus 0.2, 1.4 minus 1 divided by 2, 0.2 into 1.12 square. So T naught will be approximately 375.5 Kelvin. Right. Now they are asking what will be the Mach number just upstream of the station where temperature is 92.5 degrees Celsius. So we got T naught, right? We also know that T naught remains constant at each and every point. So at that location also T naught will be 375.5 Kelvin. So at that location static temperature is 92.5 plus 273 is equal to 265.5 Kelvin. So again we can apply T naught by T is equal to 1 plus gamma minus 1 upon 2 m square, right? T naught is 375. Sorry, this will be 365, right? T naught is 375.5 upon 365.5 is equal to 1 plus 0.2 into m square. So from here we got m is equal to 0.378, right? At that location where static temperature is 92.5 degrees Celsius, here the Mach number is 0.37, right? This can be found in another way. We have T naught value 375.5 Kelvin, right? We can apply energy equation. T naught is equal to T plus V square by 2 Cp, right? We know this, correct? This is given 92.5, right? Plus 273 is 365.5 Kelvin. This we got. We can find out V from here, right? And we have to find out Mach number. So Mach number is V by A. V we got from here. What is A? Under root gamma R T. T is given. We can find out the Mach number in this way also, right? So what is happening here? Why stagnation temperature remains constant? This concept we already discussed in the lecture, right? Using energy equation, that is H1 plus V1 square by 2. At two location we are applying H2 plus V2 square by 2, right? So let's say initially this was 2 units and this is also 2 units. So total is 4. So whatever happens with the flow, the summation of this energy will be constant for, right? So let's say temperature is decreasing. So now this became 1 unit. So obviously this will be of 3 units, right? Such that total will be constant. Similarly, at stagnation state, again it will be of 4 unit only, right? Velocity will be completely 0. Entire thing will go to in this enthalpy. Then we will write that equal to H naught, stagnation state, right? Now in the work done formula, in PV diagram, right, if process is known, right, like constant pressure, constant temperature, isentropic, constant volume, we can find out the work done by using the formula which we have discussed in the lecture, right? In one problem in assignment, straight line was given. So people were applying the work done formula for isothermal process, right? That is wrong, because when I asked them that how the graph of isothermal process look like, then they realized their mistake, that for isothermal process it is hyperbolic like this, right? So we cannot apply the work done formula for isothermal process in this case, right? In this case, what we have to do? Area under the line, integration PdV. That will be the area of the triangle and area of rectangle, right? Now in some problem, people are calculating delta S for